Hello, everyone. We are now in the next section of the book, which is sort of similar to the last section. It's more applications and things like that, but it's kind of more general. We're not going to necessarily talk about one type of application or the other. It's kind of putting into practice. If you remember in the review sections that we did, the really long video, part of it was all about how to translate words into mathematical symbols. Stuff like, is, that's a code word for equals, things like that. And so it's a little tricky. And I know this is most people's most hated part of math is word problems. But I know, and people probably tell you this and you don't believe them, but it's true. The more word problems you do, the better you'll get at them. I know no one believes me, but it's true. Because I think I was always bad at them when I was younger, and kind of one day after I just tried a lot, and I'd kind of given up on getting good at them. I just thought, I'll never be good, but I might as well do my homework, I guess. All of a sudden, just one day, they made sense, and I didn't really need a lot of help. I did them on my own. I think it was just from doing so many and practicing. So it's strange, but I think you'll get there too, as long as you do a lot of problems and practice. And be confident too. I think for some reason a lot of people they lack a lot of confidence in math. They think they're not good at it, but I think anyone can be good at math. It's just maybe you had a bad experience in the past. You had a teacher that wasn't very nice or didn't explain things very well, and you probably took it like, oh, I'm probably bad at math, when it was really just they didn't explain it very well. So I think you should have more confidence. You can do it. You're going to kick some booty, take some names. Anyway. All right, that's enough of that. So this section, there's not a lot of direction to it, I'm not going to say this is how you do all these problems, because they're all different. So it's just this up here in this red box that I drew, just kind of a general strategy for how to solve these problems. Especially if you feel like you're bad at word problems, this is kind of a good way to go about it. It seems kind of silly, I guess, if you're like, yeah, these are obvious, but sometimes they do help. All right, so the first thing you should do is just step one, familiarize yourself with the problem. Of course, just read it. I wouldn't say as you're reading it, try to write things down. Just read through it, make sure everything makes sense. You can kind of picture what's going on. I would even say if there's something to draw a picture of, like if it's something geometrical, like a triangle or a rectangle, you could draw a picture of it if that helps. Sometimes that does help. There will be one or two in this section where we'll do that. Draw a picture if it applies, like if there's a shape or something. Because there will be ones where they'll say, for an example, there's a rectangle whose length is 4 feet longer than its width or something. It's hard to come up with an equation, I think, until you draw a picture of it and label, the length is this and the width is that. So anyway, that applies to some problems, but not all. But you should familiarize yourself with the problem. And then step 2, you want to translate to mathematical language by first letting x stand for the unknown quantity. At least you can, first thing, just read through it, make sure it makes sense, and then say, what's the thing they're looking for here? They say, find this. Well, whatever this is, I'm going to let x equal that. And then I think an equation will kind of follow from that, and the other words that they use in the problem. All right, so we're going to let x be what they want, and then from there we can form an equation based on the words that we're given. And then, of course, that's always the hardest part. Step 2 is very tough. It's just forming the equation. But once you have the equation, solving it's usually good. That's supposed to be a happy face if you can't tell. And then you're going to check your answer in the original problem. A lot of times, too, you can just kind of see with logic, does that make sense, if I got 5, does 5 make sense in this problem? I guess if 5 is the speed of a car driving, that doesn't sound quite right. 5 miles an hour, that seems really slow. But if you got 60, that makes sense. 60 miles an hour, that's kind of a normal speed of a car. Things like that. And then the main thing, too, I know, and maybe in some schools that you go to or that you've gone to prior, if you just say the number in the end, like, my answer is blah, and circle it, that's fine. But this school, they definitely emphasize writing your answer clearly and using complete sentences for word problems. So that's going to be a big deal throughout all your math classes. So it's good to get used to that. I'm going to try to remember that too. All right. I guess we might as well jump in here. So let's see. The first example, what do we have here? It says 5 times the sum. And as I'm reading it, I'm keeping in mind, I remember sum means add. So something's adding 5 times the sum of, so I guess the things that are adding are going to follow the word of. 3, okay, and twice some number is 70. What is the number? Okay, there's a lot to take in there, but I think everything makes sense. All the words, I kind of know what they mean and everything. I think what I'll do first is I'm going to say, let x be the number. Kind of that, whatever unknown number they keep mentioning. They said some number or whatever. Okay, now I think as I read this problem from left to right, I'm going to start writing down what I hear, you know? Let's see. So in the very beginning, they said 5 times. So I think we're multiplying 5 by something, huh? 5 times what? The sum. Okay, the sum means you're adding a couple things together. And I'm not even going to read on. I'm just going to think, you know what? If you're multiplying 5 by the sum of two things, that really means 5 times the entire sum. Whatever these two things are added together, you're multiplying 5 by that entire thing. So you got to be careful. The order they mention things in, the fact that they said 5 times and then they said sum means you put parentheses. So be careful. It's because 5 is multiplied by the sum, the entire sum, that you have to put parentheses. Okay. After the sum, what happens? The sum of 3 and, I guess, so that means that 3 and something else is what's being added here. 3 and what? Twice some number. Okay, how does that work? Well, some number we called x, and twice something, I guess that means to double it, right? Or to multiply by 2. I think they mean twice some number, that's 2x. So far, maybe I'll read it again just to make sure, and look at what I have. It started out 5 times, okay, the sum, good, I put a plus sign, of 3 and twice some number. I think that makes sense, 3 and twice some number, yeah. All right, we're almost done here. The word is, remember that's probably the most key thing in these problems. Is code word for equals. And then what follows is just the number 70. So that must be it. Yeah, so you got to be really careful. I think this problem, it's easy to mess up and not put parentheses. But just keep in mind, if I were to not put parentheses, like if I put 5 times 3 plus 2x, you notice that 5 is only being multiplied by 3, not the entire sum of 3 plus 2x. So be careful. The language they use is very purposeful. They say the words in a certain order on purpose. So make sure you do put parentheses when you're supposed to, omit them when you're not supposed to. But it definitely takes practice and a kind of a keen ear to get the hang of it. All right, now I can solve for x. And you notice usually when you set these up, solving is not that bad. It was the setting up that was tough. All right, so now if I want to solve this for x, what do? I think in our previous sections, the steps that we took, we said, if there are parentheses, you should distribute to get rid of the parentheses. So I think that's the first thing I'm going to do here, is get rid of those parentheses. 5 times 3 is 15. And then we have 5 times 2x, that's 10x. And on the other side is a 70. Okay, if I had like terms at this point, I would probably combine them, but there are no like terms, on one side or the other. So it's time to just start solving for x. And like we talked about previously, you're going to want to get rid of what's being added or subtracted first before you get rid of what's being multiplied or divided. So I'd get rid of the 15, and since 15 is positive, I'm going to divide by 15 to get rid of it. Since 15 is positive, I'm going to subtract to get rid of it. 70 subtract 15 is 55. Is that true? Yeah. Yeah, that's a winner. All right, we're almost done. Now I just need to divide by the 10 since it's being multiplied by x. And you can kind of use, if you want, you've probably seen this before, or if you haven't, it's a good trick. Anytime you divide by 10, all you really do is you move the decimal to the left once. So, for example, 55 is a whole number with a decimal, an invisible decimal to its right. If you divide it by 10, really that just moves the decimal to the left once. So it's 5.5. Not too bad, right? Or, if you kind of you didn't memorize that, or you're kind of not thinking, or you're half asleep, you can always do long division. 10 into 55 is, 5. 5 times 10 is 50. But I have 5 left over, so I'll have to put a 0.0, bring down the 0. 10 into 50 is 5. That kind of thing. So that would always work, and that didn't take too long, but you can, if you did this, it just showed me 5.5, I wouldn't say, oh, you didn't show your work, or whatever. Don't worry about that. All right, that's a good little trick. Dividing by 10 moves the decimal to the left once. If you divide by 100, that moves the decimal to the left twice. And then 1,000, etc. It's pretty good. All right, I think we're doing pretty good here. We might as well jump into example 2. So I think this one's more complicated because what does it say? The apartments in Erica's apartment complex are consecutively numbered on each floor. So just so you know, if they say consecutively numbered, I can't even say that word. Consecutively numbered. That means, what are two consecutive numbers? I'm just making them up right now. How about 23 and 24? They're just two whole numbers that are right next to each other, that's all. So that makes sense with apartments, right? When you go down the hall of an apartment complex, every apartment number is the previous number plus 1. So it'd be like, if one of them is 432, the next one's 433. Stuff like that. Okay, so they're consecutively numbered. They say the sum of her number and the next door neighbor's number is 2409. What are the two numbers? Okay, this one is definitely more complicated because notice, first of all, they ask for two things. What are the two numbers? Whereas in the last example, all we cared about was one number. So I'm going to have to call each of them something. So the two things they're looking for is, I guess, Erica's apartment number. You could just say Erica's number. I mean, we all, in the context, we'll know what that means. The neighbor's number, I guess. Neighbor's number. So I guess since we don't know what Erica's apartment number is, we're just going to call it X, let's say. Or your favorite variable, whatever you want. Maybe E for Erica, whatever. Okay, if Erica's number is X, what's her neighbor's number? So at this point, I would not want to introduce a new variable. Like if I called the neighbor's number Y, that wouldn't really help, because imagine if I used Y. The equation we're going to get is the sum of her number and the neighbor's number is 2409. But how am I going to solve this equation when there's two variables? That's the thing, is I can't solve an equation with two variables. That's why I have to make sure that everything is in terms of the same variable. So what I want to do is see, okay, her neighbor's number. How can I use X to figure out her neighbor's number? If her number is X, what would you do to that to get the next number? That's hard to think about, but notice in this kind of specific example, we were talking about 23 and 24 are consecutive numbers. What could you do to 23 to get 24? Well, I think to me you're adding 1, right? So any number plus 1 is the next consecutive number. So I think if I want to call her neighbor's number something, I'm going to call it X plus 1. Whatever Erica's number was, plus 1. So those are the two numbers we want. And that's going to be, once we set up the equation, it won't be too bad to solve because we'll only have one variable. We only have X's here. So I think we're doing pretty good. Okay. So let me see. I think kind of the second half of this problem is going to give us the equation. The first half was just more letting us know that the numbers are consecutive and stuff like that. So it says the sum means add. Got to remember that. Okay, the sum of what? The sum of her number. Okay, her number we called X. The sum of her number and what? The sum of her number and the neighbor's next door. Oh, we called that X plus 1. Aha! So that's, hopefully that makes sense. This is her number, neighbor's number. And the sum, they said the sum of it, so you're adding them together. And then what do they say? Is 2409. Remember, is code word for equals, and then the number. Aha, I think that's it. The sum means add of her number, X, and the neighbor's number, X plus 1. Okay, we're ready. Now I've got it set up. I'm going to just rewrite it here. Okay, X plus 1 is 2409. And then I notice I have like terms on one side of the equation right away. There are two X's here. I might as well add them. And remember, you can think of them both as 1X, even though they just have an X. So this is like a 1X and a 1X. I would add the coefficients. 1X and 1X is 2X. Plus the 1 that was kind of sitting there is equal to 2409. Okay. Let me move this up a little bit here. All right, now I think I can solve this. This is the easy part, huh? All the hard part was setting it up and brainstorming. I'm going to subtract 1 to get rid of the 1 that's adding. Then you have 2x left. 2,409 minus 1 is, 2,408. And now all that's left to do is to divide by 2. And that I might be careful with. X is whatever 2 into 2,408 is. 2 goes into 2 once, into 4 twice, into 0 0 times, and into 8 4 times. Okay, so it must be that guy. Erica's number was 1204. And a lot of these problems too, you set up the equation, you solve for x, or whatever your variable is, and maybe you're not quite done yet. There might be more that they were asking for. So this is probably one of those, one of those times. What did they ask for in the very end? They said, what are the two numbers? So we found one of them, x is 1204, and remember that x, that was Erica's number. Was that her name? Erica? Yeah, I think so. What was her neighbor's number? Remember we said that her neighbor's number will just be whatever Erica's number is plus 1. So her neighbor's number will be Erica's number, 1204, plus 1, which is 1205. Which makes sense. I mean, if they're next to each other, they're consecutive numbers. So those are the ones. And you can check your answer. You could just say, okay, does it seem like the sum of those two numbers is, what'd they say? 2409? I think it is. If you add 1204 and 1205, that is 2409. Okay. And I know at this point, problems like this, there are always one or two students or more that say, hey, I think I could have just guessed the answer. Or I could have, you know what I could have done is taken the number 2409 and said, what's 2409 divided by 2? I mean, it goes in basically 1204 times. And, you know, why do you have to set up these equations? I could just do it in my head. But keep in mind, this section isn't really, I think it's just kind of, getting you ready for more complicated word problems. So we'll see more complicated word problems later in this class, and in your next class you'll see even more complicated ones. So this section isn't really about solving the problems. I think a lot of these problems can be solved just using logic or using, division or multiplication. So the algebra part is more just a practice, so it's easier later. So keep that in mind, even though you can think there might be an easier way to do this without using algebra, you want to use algebra just to get the hang of it so it's easier later with the more complicated problems. Alright, so now that that's over, let's see about this guy here, example 3. This one says, it's kind of interesting, the world's oldest bride was 19 years older than her groom. Okay, makes sense, okay. So far so good. Together their ages totaled 185. So I guess that means when you add their ages. There. Now, sometimes it kind of helps to make notes to yourself, just to kind of get closer from the words, get closer to math. When you add their ages, you get 185. That kind of helps. Sometimes it helps to write things like that down. How old were the bride and the groom? Okay, this is another tricky one like example 2, because they're not really asking for one thing, they're asking for two things. So I might assign variables to the two things we're looking for. And remember, you want to get them both in terms of the same variable. So I'm going to say, okay, I guess the first thing they mentioned was the bride, huh? So I'm going to say something is equal to the bride's age. And then the other thing they're looking for is the groom's age. Groom's age. Well, one of them you're just going to call your variable x. So let's say the bride's age is x. And how would you find the groom's age? I think there's a key part of what they told us in this problem that'll help us figure it out. You notice they said the bride was 19 years older than the groom. So I guess that means if you take, sometimes it helps to, to brainstorm too. The groom's age, plus 19 is the bride's age? Does that make sense? Yeah, they said the bride is 19 years older than the groom. So if you were to figure out the groom's age and add 19, that would be the bride's age. So you know what? Now that I think about it, maybe it would be better to call the groom's age x. And that way I think I can come up with an algebraic expression for the bride's age easier. Because what they say, the bride's age is 19, basically the bride's age is 19 more than the groom's age, which is x. So the bride's age would be x plus 19. 19 years more than the groom's. Does that make sense? I think that makes sense. Yeah, it does help for me for some reason when I kind of, I guess this right here in my red box here, it's like an intermediate step, trying to get closer from the words to the math. You know, if that helps, hopefully it helps some people, but that really helps me. So, okay, I think we got it. The groom's age is X, or you can call it G for groom. Then the bride's age is that plus 19. I think it sounds good. Okay. I think we're ready to start setting up the equation. I think the second sentence is what's going to give us the equation. The first sentence was kind of just there to let you know how to set up the variables. But the second sentence says, together their ages totaled 185 years. I remember I made this note to myself above. I said, you add their ages. So this, maybe if you don't want to, you don't have to, but this kind of helps me sometimes to write a little intermediate step here. The bride's age, whatever that is, plus the groom's age. It's going to add up to 185. I think that's what they're trying to say. And now that I kind of have that, that's an intermediate step from the words to the math. And now I'm going to go all the way to the math where I replace the bride's age. We called that X plus 19. So I'm going to replace that guy. And then the groom's age, that was what we just called X. But otherwise, I'm going to keep everything else the same. It was a plus sign, and then an equal sign, and then a 185. Okay, that was a tough one. Now I think we're ready to solve this guy. I'm going to combine like terms here. We got two x's on the same side of the equation. X plus x is 2x. And then we have that 19 as well. It's equal to 185. Okay, looking good. And yeah, now I think if you're anything like me, you'll be amazed at how easy it is from here. It just seems like the whole thing should be difficult, but it's really just the setting up. So at this point, I want to solve for x. I have a 19 adding on the same side as x. If I want to move it, I'll subtract it, the opposite. So 2x is, 185 minus 19. I don't want to make a mistake, so I'm going to be careful here. What's 15 minus 9, you guys? That's tough. 6? Is that true? I think so. 166. Okay. Okay, then. And you know, if you make a mistake, like right there, if I subtracted wrong, and sadly that's what I do a lot. All the algebra I think I usually am good with, but it's the subtraction. And I think when we kind of check our answer and see if it makes sense, we can tell it won't work out. So now I'm almost done solving for x. I'm going to divide by 2. And that'll be it. Let's see. I think I can do that one in my head. 2 into 166 is 83. I think so. Yeah, that sounds good. Okay. So I got to remember, what did x stand for again? Because that might not be exactly what they wanted. Hey, wait a second. You guys, remember how I said we should be writing our answers in sentences? And then I just totally didn't do that? Oh my gosh. You're probably thinking, what is this lady talking about? She's not practicing what she preaches. I'm sorry, you guys. I'm sorry. Let's go back and sum these up. In the first example, our answer was 5.5. So let's write that in a sentence. That was the number they're looking for. The number is 5.5. That's the kind of thing we're looking for in here. You want just to kind of sum it up so someone can see the conclusion here. And then in example 2, they were asking, what were they asking again? What were the two numbers? So this is probably where, let me erase a little bit. I did a lot of good stuff here, a lot of fun times. If I want to kind of sum it up, I'm going to say Erica's apartment number was 1204 and her neighbor's was 1205. Something like that. That's probably what you want to do. I'm sorry. Just so focused on the math, you know? The math is the fun part, am I right? Come on. Everybody knows that. Just kidding. But you know, if this was on an exam or something, I would, for every word problem you're given, I would prompt you. I would say, and by the way, make sure you write your answer in a complete sentence so you don't forget. I would prompt you. Because it's easy to forget, obviously, like I did. All right. So what reminded me is I have to remember what this number we just found stands for. Which is why it's good I wrote it down earlier. Up here where it says, in this box, the groom's age. Okay, so that means the groom was 83 years old. But then I better check, is that all they were looking for, or is there more than that? I think they wanted a little more, right? They said, how old were the bride and the groom? Well, we got half of it. if we want the bride's age, remember we said the bride was 19 years older, so all I have to do is add 19 to that previous number, 83, and that'll be the bride's age. What's that? Ooh, 102? You go, girl. Nice. Very nice. Okay, anyway. Sorry. The groom was 83 years old, and the bride was 102. That's amazing. Awesome. Was 102. Hey, love is love no matter your age. Am I right? Get that. We're getting all philosophical. Isn't that beautiful? All right. We did it, you guys. We did it. Okay. Don't worry. Only a few more. Actually, quite a few more. But you know, I think on any of these, if you ever feel like you're getting bored or these are too easy, you can kind of go ahead and try to solve them. You know, pause the video, try to solve it, and then fast forward and say, let's see if I got the same answer. And that way you don't have to sit through all my blah, blah, blah. But if you're barely hanging on and this is not making as much sense, then I think, yeah, it's probably good to go slow, huh? Okay, next example. These take a long time. I'm sorry, you guys. They won't take you as long because you're not having to explain it to someone as you do it. You're just kind of doing it as you think of what to do. All right, so a rectangular community garden. All right, right away, they mention a rectangle. I'm going to draw it. I think it helps whenever they mention any kind of shape, it helps to draw it. You can pretend like that's a rectangle. I'm trying to see if I can draw straight lines, but I'm not good at it. Okay, so a rectangular community garden is to be enclosed by 92 meters of fencing. All right, so I guess we're fencing, okay, along one side here, plus along this side, plus along this side, and along this side. So the four sides together is going to be 92 meters of fencing. Okay, and that, if you're, not too familiar with geometry, we call that perimeter. Sure. That's just the distance all the way around a shape if you were to kind of measure one side plus the other, plus the other, plus the other. Okay, so we got the perimeter. What else? They say, in order to allow for compost storage, the garden must be 4 meters longer than it is wide. Okay, so I guess we're saying, let's say this side is the length. I don't know. It's 4 meters longer than the width, which I guess is this. And since those are the things we don't know, and I think that's what they're asking for, right? When they say, what are the dimensions, that means they're asking for the length and the width. So I'm going to call one of them something. Let's say this guy, the width is x. Then the length was 4 more than the width. That means it's x plus 4. Because if you have 4 more of something, that means you have something plus 4. So I think that makes sense. All right, and I think that's all we're given, right? The perimeter is 92. One side is x, one side is x plus 4. So I think we're going to have to relate the two ideas, that the perimeter is 92 and the sides are x and x plus 4. Well, let me see. I'm going to think about what is the perimeter of this shape. How do you spell that? Perimeter. Well, I know it's 92, but on the other hand, I know that it's all the sides added together. And I know this side here, x plus 4. I know this side, x. How about the side opposite here? Well, since it's a rectangle, this length should be x plus 4 as well. It should be the same as the length across from it. And then how about the length of this side? Should be the same as the length of the side opposite to it. So whatever one side length is, the side opposite of that should be the same length. So the perimeter, since the perimeter is all 4 sides added together, the perimeter is going to be, it doesn't matter which side you start with, I'll just say the x plus 4, that was one side, plus, what was the next side we wrote? X, plus, the next side we wrote was the one across, x plus 4, and the very last guy was x. So let's say this is like side 1, this is side 2, side 3, side 4. And perimeter again means you add them all together. Added. We don't quite have an equation yet because I do see a bunch of x's, but I don't want to see p. But hey, I can replace p because I know the perimeter is 92. Aha! So 92 is the perimeter, and that must be equal to all this crazy junk on the right side. X plus 4, which was the first side, x, which was the second side, x plus 4, which was the third side, and then x, which was the last side. I think we can solve this equation. It looks complicated, but you notice the right side has a lot of like terms. How many x's are there? 1, 2, 3, 4. Okay, we got 4 x's. And then what's left over? This 4 and this 4, they add up to 8. All right, that looks a lot better now that we've kind of combined like terms, huh? All right, if I want to solve this, I'm going to move the 8 over first. Since 8's adding, I'm going to subtract it to get rid of it. 92 minus 8 is 84, I believe. Okay, now if I want to solve for x, I just need to divide by the 4 there. Divide by this guy here. And it's a good sign that it goes in evenly. That's not always the case, but in this problem I think it makes more sense. You want probably your garden to have a whole number of length and width. 4 into 84 is 21. All right. And then that, again, that's not enough to just end there, because we want to know, what does x even stand for? It looked like in my diagram I made x be the width. But what was everything measured in? Are we talking about feet here? Are we talking about miles? Or now when they mentioned 92, they mentioned meters. So that must be the dimension there. That was the width. Okay. But they want dimensions, plural. So we want the width, but also the length. But remember, we said the length was 4 more than the width. So it'd be the width, which was 21 plus 4. That's 25 meters. All right, I think we found both of them. The two answers we want are 21 and 25. But we better write it in a sentence, right? I learned my lesson. I almost forgot on the other ones. All right, so the width of... I don't even remember what we were talking about. Oh, the garden, that's right. The width of the garden is 21 meters, and the length is 25 meters. And if you want, you can use abbreviations. You don't have to write the word meters out. You can actually write M for meters. That's up to you, yeah. But that's what they really want, is that last sentence. There we go. That was a lot of work to get there, but it was totally worth it and so much fun. Am I right? No, I'm not. Yes, I am. Come on. Okay. Talking to myself. That's not good, huh? Okay. That was fun, you guys. Next example. You know, it seems like a lot of examples. I thought about doing less, not this many, but I figured if you get the hang of it, you can probably, go ahead and try them on your own just to get the hang of it on your own. And if you don't get the hang of it, then it's actually good we're going over a lot. So I know this video is a little long, but I figure, yeah, if you get it, you can kind of try the problems on your own. If you don't get it, then you really want to see all these examples. All right, anyway, that's enough of that. Next example, example 5. So a lot of these, they talk about geometry and things like that. This one's talking about angles. So they're saying the second angle in an architect's triangle. Ooh, triangle. I'm going to draw a triangle. And don't really worry, they're talking about angles, so I'm thinking, oh wait, do I have the angles right? Did I make those angles too wide or too narrow? Whatever. It's just, the diagram's just kind of there so I can label it better. They're talking about second angle, it's something larger than the first, and then they're talking about the third angle. So maybe I'll label them. This is maybe my first angle. Doesn't really matter which one's which, right? This is my second angle, and this guy will be the third angle. Okay, let's see if we can give them some kind of names. But let me read the whole thing just to make sure it makes sense. The second angle of an architect's triangle, okay, that's this one they're talking about, is 30 degrees more than the first, which is this guy. Okay. The third angle is 30 degrees more than the first. Huh, okay, interesting. They want you to find each angle's measure. So if it's like 20 degrees and 80 degrees, that's what they want. So I think, you notice when they're talking about the first angle, the second angle, and the third angle. First, second, third. When they talk about the second angle, they're referencing the first, right? They say, the second angle is 3 times as large as the first. And then when they talk about the third angle, they're also referencing the first. It's 30 degrees more than the first. So I think maybe I'll call the first one something. And that way, when I reference it, I can just keep referring to it as the variable x. So if the first angle is x, what do they say about the second one? The second angle is 3 times as large as the first. So 3 times as large as the first, that's 3 times x, huh? Since the first was x. 3 times x. Yeah. Makes sense, all right. And then what do they say about the third one here? The third angle is 30 degrees more than the first. So 30 degrees more, that means you're adding 30 to something. 30 degrees more than what? The first. That was x. I think that sounds right, huh? If I say the first is x, the second was 3 times, okay, yeah, it means 3 multiplied by. And then the third one was 30 degrees more. So if I have 30 more of something, that means I'm adding 30. I think that makes sense. Okay, let me label these guys. The first angle was x, the second angle was 3x, and the third angle was x plus 30. Gotcha. All right, we got everything labeled. It looks good. They want us to find the measure of each angle. And thankfully they give us this hint, because not everybody knows this. The sum of the angles in a triangle, remember that means add, so I guess they're saying if you add all 3 angles, you're going to get 180. I think that's going to give us the key to this equation. So they're saying if you add all 3 angles, the first angle, again, this is kind of like my intermediate step. If you're ready to write the equation, then that's good. But if you want to be careful about it, this is a good way to go. The first angle plus the second angle plus the third angle. They said all 3 angles added together has to be 180 degrees. And if you want to, you could write the degree symbol, but you don't have to. If we just kind of keep in mind everything's in degrees, then we don't really have to write it. All right, now that I have it kind of written out, sort of in between words and math, now I'm going to replace first angle, we called that guy x. The second angle we called 3x. And that third angle was x plus 30. So this was this, this was this, this was this. That should be 180. Aha, we have it, you guys. We did it. Well, we have to solve it, but we did the hard part. But now to solve it, I have a lot of like terms over here. X plus 3x plus x, that's 5x. And then the 30, he's the only constant on the left side, so I'm just going to have to say plus 30 equals 180. All right, I think I can solve this. I've done this a million times, huh? Move the 30 over first. Now that we have 5x by itself, it'll be equal to 150. And all I have left to do now is to divide by 5. So x must be 150 divided by 5, which is 30. Aha! Now this is where I got to remember, what the heck did x stand for again? What was the angle, the first angle? Aha! So that means the first angle must have been 30 degrees. All right. But they didn't just want the first one, they wanted the second one and the third one. Second. Remember, we labeled the second one as 3x. So if x is 30, 3x is, just replace x here with 30, since you know x is 30. So it must be 3 times 30, which is 90 degrees. All right, we're almost there. The third angle, that was the one we said was x plus 30. And x, again, we found x was 30. So it's 30 plus 30, which is 60. There we go. We got all 3 angles. Now, if I want to, I can sum it all up kind of in a sentence. I'm going to say, and I think because it's a triangle, you can twist a triangle around and you don't really know which is the first angle, which is the second angle. So really, it doesn't matter which one's which. I'm just going to say the 3 angles were blah, blah, blah. I don't think you really have to say the first was this, the second, The 3 angles were 30 degrees, 90 degrees, and 60 degrees. I guess a quick check would be just make sure, do all 3 of those numbers, do they add up to 180? 30 plus 90 is 120, plus 60 is 180, yeah. All right, I think we got it. Yay! Okay, calm down. All right, so I think we're almost there. The only thing left to do is these 2 problems that are talking about distance, rate, and time. So these problems are actually pretty difficult. If you've kind of heard people joke about those problems where they say, a train left the station at 12 p.m. and it was going 50 miles an hour due south, and those are complicated problems, but these are kind of the beginning steps to being able to solve those ones. And you'll see these again, they'll get more complicated, and you'll see them in your next class. So it's just good to have seen them in this class. So we got distance, rate, and time, and the key formula we're going to use is that distance is equal to rate times time. And keep in mind, a rate is just another word for speed. So if they said, oh, I was driving 5 miles an hour, or whatever it is, then that's really the same thing as rate. Speed and rate are the same thing. And then distance would be, miles. I drove 5 miles. Time is how long it took you. Oh, I drove for 10 hours, whatever it is. All right, so what are they saying here? Trung rode for 1/2 hour on the train and then for 1/3 an hour on the bus. The speed of the train was 50 kilometers per hour faster than the speed of the bus. If he traveled a total of 37.5 kilometers, what was the speed of the bus? Okay, that's a good one. These are very tricky, these distance, rate, time ones, and this is why I made sure to put a little table here. So these are, the table's invaluable for these problems. It's very important. I think the first thing you want to do on these is label the parts of the trip on the table. The parts of the trip. Because every problem's different. In this one, they're talking about, he took a train and then he took a bus. So maybe I'll say, on one hand, he took a train. On the other hand, he took a bus. And then we'll try to fill in the distances for each or the rates for each. And all right, so we've labeled those. And then from here, there should be one of the 3 things are given. Either you're given both distances, or you're given both times, or you're given both rates. So I want to now fill in the given values for distance, rate, or time. It should only be one of those you're given. I think in the very beginning of the problem they said he rode for 1/2 an hour and then he rode for 1/3 of an hour. That's time, right? 1/2 an hour, that's time. Okay, so under time here I'm going to put 1/2 an hour for the train and 1/3 of an hour for the bus. Okay, so every time they give you a problem like this, there should be just one thing that you can fill in right away. And then let's see, the next thing is it should give you some kind of relationship between another variable, like the distance on the train was 10 more than the bus, or his speed on the train was 10 more than the bus, something like that. So you want to fill in with a variable a given relationship between one of the remaining guys, D or R or T. I'm not going to use T because T is already filled in with the 1/2 and the 1/3, but now I've got, okay, did they give us a relationship between the 2 distances or the 2 times? Well, the second sentence, what are they saying here? The speed of the train. Okay, speed means rate, so I think we're talking about rate here. The speed of the train, which is this guy here, was 50 kilometers per hour faster. Okay, so something about 50. 50 kilometers per hour faster. Faster is more, right? You're adding 50 to something. 50 more than the speed of the bus. Okay, well, I don't really know what the bus's speed was, so I'm going to call it X. So if his speed was X, the train speed was 50 kilometers per hour faster than that. So whatever the speed of the bus was, X plus 50 more than that. All right, I think we're good. We're doing good here. We got time filled in, we got distance filled in. We got time filled in and rate filled in. And then the last thing to fill in is distance. And then, let's see, you're going to use, the last thing to fill in, you're going to use the formula to fill that guy in. Distance, rate, time to fill the last column. Because at this point, you should have already filled in 2 of the 3, distance, rate, and time. The last thing you're going to use the formula to fill in the rest. So since distance is equal to rate times time, for example, if I focus on the train, the distance that the train traveled is its rate times its time. That's 1/2 times its rate was X plus 50. So notice I'm just taking what was in the rate column and the time column and multiplying them, since the formula says distance is equal to rate times time. And the bus is similar. The bus, his distance is equal to his rate, which was X, times his time, which was 1/3. So X times 1/3 or 1/3 times X, that would be the distance, since distance equals rate times time. Okay, whew. This is tough. It's tough stuff, but again, I think they just want you to have seen this before so it's easier later. And then I guess the only piece of information we haven't used yet is that he traveled a total of 37.5 kilometers. And usually the last piece of information is what's going to give you your equation. Write an equation based on the last piece of information. All right, what'd they say? They said he traveled a total of 37.5 kilometers. Okay, I got to keep in mind, kilometers is a unit of distance. So he drove his total distance that he... This is kind of me brainstorming right now. His total distance, I think they're talking about for the bus and the train put together, was 37.5 kilometers. Okay, and I think what I want to do is relate 37.5 to the things we have in the box there. Well, his total distance, that was his distance for the train distance plus the bus distance. Because that's all he took was the train and the bus. Total together should be a distance of 37.5. Okay. But the train distance, we gave that a name, right? Above in the box, we said the train distance was, what was it? Here in the red, 1/2 x plus 50. That was one of the last things we filled in the formula. And the bus distance, if I look at the last row of that box, the distance for the bus was 1/3 x. So I'll fill those in. It says those together, atom, is 37.5. Aha! You know, that only took like half an hour, right? Setting up that equation. But I promise, it gets easier the more of these you do. And again, this is just, I think they're just trying to get us ready for more complicated ones next semester or in the next class. All right, so now I have to solve this. Oh God, this looks complicated. But remember, one of the tricks we had for solving an equation that has a bunch of fractions, in a previous section we said, you know, if you see more than one fraction, what you want to do is multiply by the LCD. So here, if I look at this equation, I got two fractions here, 1/2 and 1/3. Between their two denominators, the LCD would be 6, right? Like if I had 1/2 and 1/3 and I wanted to find a common denominator, what I would do is try to get them to be 6. But if you remember, when we used this trick, we didn't use the LCD to try to get them to have the same denominator. We used the LCD just to simplify it. So we're going to multiply this entire equation by 6. And that should make it look simpler and there'll be no more fractions. Because I'm not really getting excited about multiplying this 1/2 in here. But it's going to be a lot easier. So I'm going to take this 6 and multiply it by each term. 6 times the 1/2, 6 times the 1/3, and then 6 times this 37.5. And that'll do it. All right. And you know, just to be safe, I think what I'll do is I'm going to write 6 times the first thing, 6 times the second thing, and 6 times the third thing. And then look at what's going to happen between them. So it's 6 times the first guy, 1/2 x plus 50, plus, okay, 6 times the second guy, that's 1/3 x, equals 6 times the last guy, 37.5. All right. So I think it's going to look good. This is a good trick. It looks complicated now, but it's going to look simpler. So what I'm going to do is put 6 over 1 and reduce. 2 goes into 6 3 times. So this fraction times this fraction is just a 3 times whatever was left over in the parentheses, which was x plus 50, right? X plus 50. All right, that looks a lot better. I'd rather have a 3 there than a 1/2. And then here, if I put this 6 over 1, 3 goes into 6 twice. So these two fractions multiplied together just becomes a 2. Then, of course, you still have the x left over, so plus 2x. And then on the right side, this is something where I'd probably have to go off to the side and figure that out. Let's see, maybe over here. 37.5 times 6, let's see. Well, 6 times 5 is 30. 7 times 6 is 42, plus 3 is 45. Carry the 4. 6 times 3 is 18, plus 4 is 22. And then since there's one digit beyond the decimal, I have to put the decimal with one digit beyond it. So it's 225. That's pretty good. That's not the worst number I ever saw in my life. Okay, this looks a lot better. I'd much rather deal with this. I do have to distribute this 3 though. 3 times x, 3 times 50 is 150. Then you have a 2x here. Okay, whoops, I put plus, it's an equal sign. There are some like terms, 3x and 2x make 5x plus the 150 equals 225. The next step would be to move that 150 over. I'm going to subtract it in an attempt to try to get x by itself. Let's see, so if I move 150 over, what's left over? 5x equals, let's see, 225 minus 150 is 75. Okay, so the last step, I kind of ran out of room here, is to divide by 5. Let's see. 5 can go into 75 15 times, I think. Yeah, 15 times. So x must be 15. Oh my goodness. I don't know about you, but after all that work on this problem, I already forgot what I was trying to do. What was x again? I gotta go back. Oops, hello, I went too far. X, okay, remember in this table, x was here. X is the speed of the bus? Okay, so we found the speed of the bus. Is that what they were asking for? Oh, thank God it was. What was the speed of the bus? Whew! And they were talking about, I was going to put miles per hour, but notice in the problem they were talking about, oh, dang. Sorry about that. Yeah, remember in the problem they were talking about not miles per hour, but kilometers per hour. So it must be, the 15 is the speed of the bus in kilometers per hour. The speed of the bus was 15. And you're okay to use abbreviations. You could put kilometers per hour like that instead of, you know, write it out in words. Kilometers per hour, blah, blah, blah. Oh my gosh, you guys. That was a tough one. So if you're burnt out, you can, you know, go off, take a break. Don't worry. Come back. But here's one more. I think this one might be a little easier. These are very tricky, these distance, rate, time problems, but the more of them you do, the better you get at them. And you know, if it doesn't make perfect sense right now, don't feel bad. I think that's normal. If this makes perfect sense, maybe you're kind of weird, right? No, just kidding. Maybe you're kind of too good at math and it's freaking everyone out. But yeah, I think the first time I learned about these problems, I didn't understand a word of it. I just tried my best, and you know, the more of these problems I saw, the more I tried, the better I got. So don't feel too bad. Just do your best. You know, try them as best you can. Maybe work on them together if you can't figure it out. But I wouldn't give you one too complicated. Like, yeah, it'd probably be, this one's a little better. This one's probably a lot nicer than the last one. Okay. So I'm going to read this problem and just make sure it makes sense. Jose paddled for 3 hours upstream and then for 2 hours downstream. Okay, that makes sense. His speed upstream was 10 miles an hour slower than his speed downstream. Okay. If he traveled a total of 30 miles, how fast did he travel downstream? All right, it makes sense. But okay, just like in the last example, since this is a distance, rate, time problem, I'm going to want to try to label the parts of the trip. So what are they talking about? I guess they're talking about upstream and downstream. Maybe I'll write that. Upstream, downstream. Just so you can kind of know which one's which and you don't mess up where you put your numbers. All right, so we're going to use the same steps that we had in that problem above. If you remember, the first step was to look through the problem and see if one of the three is just straight up given to you. Did they just give us both distances, or did they give us both rates, or did they give us both times? Let's see, paddled for 3 hours upstream and then 2 hours downstream. Those are times, right? Hours. So 3 hours upstream, 2 hours downstream. So that's my second step, is to fill in just what was given. All right, and then if you remember, the next step is whatever's left over, we have distance and rate left. They should give us a relationship between either the two distances, like one was 5 miles more than the other, or something like that, or the rates, like he paddled 10 miles an hour faster one way than the other. So the second sentence of this problem says, his speed upstream, okay, speed is rate, so I think we're going to be looking at rate now. His speed upstream was 10 miles an hour slower than his speed downstream. Okay, because they're referencing downstream when they're talking about upstream, I'm going to call downstream something. Let's say x. So that way his upstream speed, it was 10 miles an hour slower. Slower I think would be minus, right? Because it's 10, basically they're saying 10 miles an hour less than his speed downstream, which we called x. I think that makes sense, right? His speed upstream was 10 miles an hour less than his speed downstream. Yeah, okay. Looks good. And then if you remember, the last thing you're going to fill in the very last one, which I guess distance is left, by using the formula. And this formula, if this were on a quiz or a test, I would give you this formula. You know, you don't have to memorize this guy. So we're going to fill in the last two things in this table with that formula. If I focus on upstream, his distance upstream is at the rate upstream, which was x minus 10 times the time. So his distance was 3 times rate x minus 10. There it is. And then similarly for the downstream, his distance is his rate, which was x, times his time, which was 2. So x times 2 or 2 times x, whichever one you want to think of. That's his distance downstream. Okay. This is going a lot smoother than the last one, huh? Because we're getting a little more comfortable with it. All right. And then to set up your equation, the last sentence, they should give you some relationship between the last two things you filled in. Like, I just filled in the two distances. So it says he traveled a total of 30 miles. That's distance, right? Yeah, distance. So they're saying his total distance was 30 miles. But his total distance was his distance upstream. Distance upstream plus his distance downstream. Because he only went upstream and downstream. He didn't go anywhere else. So this total distance was his distance upstream and his distance downstream. And in the table, we called the distance upstream 3 times x minus 10. And we called his distance downstream 2x. So those totaled together, in other words, those added together, should be 30. And there's our equation. Oh man, we should have left off with, or started off with this one, huh? This one's a lot easier. You want to solve this guy. Whew, this is not pretty, huh? Or the last one wasn't pretty. This one's all right. If I want to solve this guy, I'm going to distribute the 3 here. 3 times x, 3 times 10, or negative 10. And then I've got a 2x here and a 30 there. I've got a few like terms on the left side. 3x and 2x make 5x. And then the minus 30. Okay, let me see. I'm going to solve for x, so I want to get rid of this 30. Since it's subtracting or negative, whichever way you want to think of it, you want to do the opposite to get rid of it and add it. That way 5x is 30 plus 30 is 60. And we're almost done. All I have to do now is divide by 5 to isolate x. So x must be 60 divided by 5 is 12, I believe. Whew. And 12. This is where I gotta remember, is x, whatever, I don't even remember what x was, but is that what they asked for? X stood for, let me look back at my table here. X was filled in this box. That's the rate or speed downstream. Downstream. I gotta remind myself of that. Is that what they were asking for? They asked for, in the very end of the problem, how fast did he travel downstream? Yeah, that's what they wanted, speed downstream. All right, so I'm almost done. All I need to do is kind of sum it up with a sentence now. Jose's speed downstream was 12, and you want to put units, so what kind of speed were they talking about up there? Miles per hour, that's right. That's what we want. Yay, we did it, you guys, in under an hour. All right, sorry if that was kind of painful. It might have been even too over explanation, you know, but hopefully it made sense and you didn't get too bored. And again, if it didn't make perfect sense, you know, you don't feel like a word problem master, don't worry. I think that's a normal feeling. Just the more of these you try, the better you'll get. And the more of them we go over in the future, the better it'll make sense. So just stick with it, and we'll move on to more things that don't have word problems if you're kind of not enjoying the word problems. But all right, I'll see you in the next video. Have a good day. I'll see you later.